The next speaker is Tomoyuki Arakawa from RIMS, who will talk about symplectic singularities and vertex algebras.
Thank you very much. I'd like to thank the organizers for this opportunity. So I'd like to talk about some connection of vertex algebras with symplectic singularities as well as the higher dimensional quantum field theory. So let me start with symplectic singularity. So this notion was introduced by Beauville. So it's a normal variety which admits closed holomorphic symplectic two form on its smooth part. And for any resolution, this pullback of this two form extend to the whole resolution. So this doesn't require that this pullback is the symplectic. And you can replace this any by 1. And so if X is a symplectic singularity, then it automatically becomes Poisson. And Poisson bracket is just defined by the Poisson bracket defined on the smooth part by extend by using the normality. And this symplectic singularity often appear in representation theory. And let me show you some examples. So of course, smooth holomorphic symplectic variety is of course trivially symplectic singularity. And if G is a complex simple Lie algebra, then its nilpotent cone is a symplectic singularity, and its smooth regular part is the principal nilpotent orbit, and the symplectic form on it is just a usual Kirchhoff constant Sourial symplectic form. And then you can consider the Springer resolution, and then pullback is just a usual standard symplectic two form on the cotangent. So this is, sorry, this is not N, but B of the flag variety. And more generally, normalization of any nilpotent orbit closure is known to be a symplectic singularity. And so definition looks maybe too abstract, but there's an easy way to construct symplectic singularity from non-one. So if you can find the finite subgroup in the automorphism which preserves the symplectic two form, then its orbifold becomes automatically a symplectic singularity. So you can, for example, do the following. You can start with your favorite complex reflection group, for example, wild group, and then which is defined, which is generated by reflections in some vector space, and a cotangent to this vector space is naturally symplectic vector space, and the diagonal action of this complex reflection group preserves the symplectic form. So in this way, you can get the symplectic singularity associated with the complex reflection group. And affinization of Nakajima-Kubiya varieties gives a large family of symplectic singularities as well. And so So this is from these examples you can see that it's closely related with representation theory, but it's also related with higher dimensional quantum field theories. For example, if you consider three-dimensional n equal 4 gauge theory, then Higgs and Coulomb branch, or their normalization, are supposed to be symplectic singularities. So Higgs branch is defined by the usual Hamiltonian reduction. And the Coulomb branch was difficult to understand, but it was defined by Bravema, Finkel, and Nakajima for almost all cases now. And for this, it was proved by weeks that they are indeed symplectic singularities. And the Higgs and Coulomb branches of one theory can look totally different, but there are very interesting duality between them, which is called 3D mirror symmetry or symplectic duality. And so which says that the Higgs branch of Higgs branch of one theory is isomorphic to the Coulomb branch of the mirrors theory. And also the category O of natural quantization of Higgs and Coulomb are causally dual to each other, which is a statement of symplectic duality. So this is a case of three-dimensional theory, and also it's known that the Higgs branch of 4D n equals 2 superconformal field theory is also a symplectic singularity as well. And in fact, you can go from 4D to 3D by doing what physicists call S1 compactification, and it's known that the Higgs branch remains the same. And if you use 3D mirror symmetry, so 4D Higgs branch of the is isomorphic to the Coulomb branch of the mirror to the 3D reduction of 4D. And so now I'd like to explain these notions related with vertex algebra. But before doing that, I'd like to make some comments on vertex algebra. So vertex algebra were introduced by Borchers and Frenkel, Rapolsky, Newman, and as certain. So I'm not going to give a definition of vertex algebra, but this you can think these as certain cousins of or a generalization of affine Katsumori algebras, and they originated in two-dimensional chiral conformal fields. So there's, unfortunately, I was talking about 3D and 4D quantum field theory, but they are not rigorously mathematically defined. But for this two-dimensional conformal field theory, so you can use vertex algebra to rigorously define this physical. And this notion has been quite successful. So first of all, it was used by Borchers in his famous proof of Moonshine conjecture, which states some remarkable duality between modular forms, modular function, and monster group. And it was shown by Yonchan Zhu that if vertex algebra is very nice, then the character of a V module from a vector valued modular form. So you can regard, by this theorem, you can regard vertex algebra some kind of algebraic framework to study a modular form. So this beautiful theorem was proved by Yonchan up to congruence property, which was proved much later by Dong. And Also, if vertex algebra are very nice, then the category of V module form a modular tensor category, which so that it gives rise to the invariance of three manifold for free. But of course, it's very difficult to find a very nice, very nice vertex algebras. So, so this very nice vertex algebra are those which are so-called rational and least or Shizuku finite. And rationality means that the vertex algebra has only finite many simple modules, and any representation is completely reducible. And the least condition, or Shizuku finite condition, was introduced by Yon-chan. And so this is defined. So you can associate certain Poisson, finite dimensional Poisson variety to any vertex algebra, and the condition says that this variety has to have dimension 0. So typically this means that the variety is just a point. And a basic example of a very nice vertex algebra is the integrable vacuum representation of affine Katsumi algebras. So this very nice vertex algebra are kind of a generalization of integral representation of Katsumi algebra. Now, but today I'd like to talk about vertex algebra which are not necessarily very nice, because there are some vertex algebra which are not very nice, but they are nevertheless very interesting, particularly in connection with higher dimensional quantum field theories, which I'd like to explain now. So let me start with the connection with 3D gauge theory. So the basic conjecture is the following. So you're supposed to associate a vertex algebra called A twisted boundary VOA to any 3D n equal 4 gauge theory, whatever it is, which knows both Higgs and Coulomb branch in the following sense. So Higgs branch is recovered by as the associated variety of this A twisted boundary VOA. And Coulomb branch is recovered as the spectrum of extra algebra of the vertex. So, so this is V. The first one should be VT. So this is quite remarkable. And also, if you use 3D mirror symmetry, this statement can be equivalently stated. Yes. What is associated variety? It's a spectrum of Poisson. So Yon-chan's associate a finitely generated Poisson algebra to any vertex algebra, and you just take a spectrum. It's very easy to define, but I'm not going to give you definition, but I can explain first. Boundary and you can equivalently state this conjecture by exchanging Coulomb and Higgs, but if you consider boundary VOA associated with the dual theory to the theory. Any more question? It's not. And there's also similar, not similar, but a connection with vertex algebra with 4D theory. So this was discovered by this group of physicists being Demos, Biendo, Peters, Brasteli, rather recently. So they define a map or certain functor from the category of 4D n equals to superconformity theory, whatever it is, to the category of vertex algebras, which you identified with the category of two-dimensional conformal theories, which enjoys the following property. So this 4D theory is extremely rich theory, and it has several interesting mathematical invariants. And one of them is the so-called Schur index, which is certain numerical invariance of vertex for this theory, which is just a Q series. And this Q series is recovered as a character of the vertex algebra. So vertex algebra is, I cannot point. Vertex algebra is in particular a graded vector space. So you can associate to each vertex algebra just counting the dimension of each homogeneous component, and then you get some Q series, and the statement is that this Q series is the same as this important index of the for this. So this is very nice because in 4D theory, the Hilbert space, so there's no large algebra which makes its Hilbert space a reducible representation over it. So it's defined as an infinite direct sum of finite dimensional representation of some finite dimensional superconformal algebra. But so the vertex algebra is a reducible representation of itself over itself. So you can use representation theory of vertex algebra to compute this important. And yes. So this is a physical statement because 4D theory is not defined mathematically. Physically, yeah. You just restrict to the R2 in R4, and then you take some BRST. And miraculously, you get difference. You just no. Any other question? And so this is quite interesting map. And so one of the property of this map is the following. So there's a notion of central charge in physical theory, which takes positive value for unitary theory. And for this case, you can consider two central charge, the central charge for 4D theory and central charge for the 2D theory, which is the central charge for vertex algebra. And these two are related by this formula. And because of this minus sign, this means that if you start with unitary theory, which is always the case for physical theory, you end up with non-unitary theory. So the image, the vertex algebra appears coming from 4D is never unitary. So this is weird. And this means that this map is not surgical. And if you look at this, so this goes to 4D to 2D theory. So you might think this loses a lot of information, but what is expected now is that in fact it doesn't. So it's expected that this map is a finite map, which means that the fiber is a finite set. So this means that the vertex algebra is almost a complete invariant of the 4D theory. So this is remarkable if you think about the 4D theory is not mathematically defined, but vertex algebra is a rigorous mathematically defined object. And if it's true, then you should be able to recover many things about 4D theory up from the vertex algebra that you get from 4D theory. And conjecture usually one of the geometric invariant Higgs branch is recovered as the associative variety of the vertex. Okay. And so you can consider the map of assigning Higgs branch to 4D theory, but this is not a finite map because there are infinitely many 4D theory which has a point as Higgs branch. So in this sense, so this conjecture is widely accepted in the physics community. So I think this should be true. So vertex algebra can be regarded as a refinement of the Higgs. And I'd like to comment on 4D mirror symmetry proposed by Peng Shan and Dan Xie and Wenbin Yang because I find it very exciting. So I was talking a little bit about 3D mirror symmetry. So you can ask the same question for 4D theory. But so in the case of 3D theory, Coulomb and Higgs branch are symmetric. They're both hyperkähler cones. But in 4D setting, Higgs branch and Coulomb branch are not symmetric. So Coulomb branch is a special Kähler geometry or Seiberg-Witten geometry. For example, the class S theory, which I'll talk about later, on a Riemann surface, its a Coulomb branch is known to be a modular space of Higgs bundle on the Riemann surface, which was proved by Gaigotom and Knightsky. So it looks like a Coulomb branch is a richer than Higgs branch. And so you can't really expect there should be a duality between Higgs and Coulomb branch in 4D setting in naive sense. But the vertex algebra is a beta invariant than a Higgs branch. And what is expected is that there should be certain duality between vertex algebra and the Coulomb branches. And so I think Wenbin is going to talk about this next week, so if you are interested. So this is very exciting new development. And so I didn't define vertex algebra and associative variety, but so kind of associative variety of vertex algebra kind of a classical object associated with vertex algebra. So we call vertex algebra a chiral quantization of Poisson variety if its associative variety is isomorphic to this one. And a typical example is the vertex algebra associated with Katsuburi algebra. So this kind of, what did I do? Induced representation starting from Katsuburi algebra has a natural structure of a vertex algebra and called universal affine vertex algebra. And in this case, associative variety is just a dual of G, which corresponds to the fact that the Katsuburi algebra is an affinization of simple Lie algebra. And previous conjectures by physicists says vertex operator algebras A twisted three boundary VOA or vertex are coming from 4D, a chiral quantization of the corresponding Higgs branch or Coulomb branch, which is supposed to be symplectic singularity. So these vertex algebra are all chiral quantization of some symplectic singularity. So you can ask what kind of property this vertex algebra have. And the statement is that if vertex algebra is a chiral quantization of symplectic singularity, then so in general, this has infinitely many simple modules. But if you look the statement is that there exists only finitely many simple ordinary representation. And ordinary representation means those modules whose character makes sense. So these representations are positively graded, and each homogeneous component are finite. And so in general, this one may have infinitely many simple modules, but if you are only interested in those whose the character makes sense, then there exists only finitely many. And moreover, those characters converge to a holomorphic function in the upper half plane, and they satisfy a differential equation called modular linear differential equation. So modular linear differential equation is kind of a differential equation that modular forms satisfy. So in particular, the solution space of MLDE is invariant under the natural action of the modular group. So this states some modularity property of the character of a modular vertex algebra. So if you recall the fact that the Schur index is the same as the character of a vertex algebra coming from 4D, so this previous theorem states out certain modularity property of the Schur index of the 4D theorem. And so this doesn't follow from previous theorem, but the normalized, this character of, this vertex algebra is often quasi-modular if it's not modular, which means that the character is contained in the ring generated by second Eisenstein series on fourth and sixth. So if it's modular, it's contained in the ring generated by E4 and E6, but for quasi-modular, you just add E2. So the character is a very interesting function. So let me explain some basic example of chiral quantization of symplectic singularities. So as I already explained, integral vacuum representation of Katsumudi algebra is very nice. So that the associated variety is a point. And point is a trivial symplectic singularity. But however, this does not come from 4D theory because this is unitary. So if you want something that comes from 4D theory, you have to consider more general representations. And there are natural candidate for such general representation. It's called Katsuwakimoto admissive representation. So this vacuum representation whose level is some rational number satisfying certain conditions. And for this, one can show that the associated variety is a nilpotent-Dobik closure, which is a symplectic singularity if it's normal. So this is really similar to the situation of associated variety of primitive ideas of enveloping algebra of finite dimensional algebra D. And they do come from 4D theory if they are boundary. Boundary means, so there are some condition for the numerator and denominator for this fractional levels. And the boundary means numerator must be as small as possible. And also, there are very interesting series of Lie algebra called Deligne exception series, which is just a series A1, E2, D2, D4, E4, E6, E7, E8. And at the level minus a check with dual Coxeter number, a check with a dual Coxeter number over 6 minus 1, one can show that the associated variety is a minimal nilpotent of closure. And these one do come from for this theory if G is simply raised. So this is actually the first example of the vertex algebra coming from 4D described by BMO. So this Deligne XML series also appear in the theory of elliptic fibration. So elliptic classification of isotrivial elliptic fibration has been classified by Kodaira, and it's labeled by the simply raised family member of this Deligne XML series. And if you can, physicist applies F theory, so-called F theory to elliptic fibration to get some 4D theory. And these are exactly the vertex algebra coming from this 4D theory. And also, there are nice family of vertex algebra called the double algebra. And their associated variety is a nilpotent Schroders slice, which is the intersection of Schroders slice and nilpotent oblique closure. And they do come from 4D theory, the level is boundary. And so I listed some example of associated variety, in particular the Katsumuri algebras, but this actually quite difficult to determine. So determining the associated variety remains widely open, even for the irreducible vacuum representation of Katsumuri algebra outside of the admissible levels. And there was not even a conjecture, but recently Pen Shan and Wenbin Yang and Tishan Zhou proposed a very nice conjectural description of vertex algebra, associated variety of this affine Katsumuri algebra from the perspective of 4D mirror symmetry, which I think Pen is going to talk tomorrow. So now I'd like to talk about the vertex algebra coming from the so-called 4D theory called theory of class S, where S stands for 6. So this even come from a higher dimensional, 6-dimensional theory. You consider 6-dimensional 2-0 superconfirmed field theory on R4 times punctured Riemann surface, and you fix punctured Riemann surface or make it very small. And then you get some 4D theory, which of course depends on the punctured Riemann surface you choose. So this is indexed by this punctured Riemann surface, and also the Flavor symmetry group G, which is a semi-simple group. And so as I already mentioned, the Coulomb branch on R3 times S1 of this theory is known to be a moduli space of Higgs bundles on this punctured Riemann surface. And also the Higgs branch is also very interesting. And it's known to be Moore Tachikawa varieties, which was introduced by Moore and Tachikawa up to certain mathematical conjecture, which was proved by Ginzburg, Kazdan, and Brovellman, Finkelberg, and Nakajima. And this is a new family of symplectic varieties which satisfy the following properties. So maybe So one of the statement of Moatachika is that it's compatible with the gluing of Riemann surface. So it's enough to describe them for genus zero cases. And for genus zero cases, so if I denote MTGR, the Higgs branch for the genus zero Riemann surface with R punctures, then, so this one is a symplectic variety with R commuting Hamiltonian action of this group G. R is a number of punctures. And there are some initial conditions. For two punctures, it has two commuting action of group. And cotangent to G is obviously have two commuting action. And the condition is that this should be the same. And for 1 point, it should be a product of G and constant Slode slice, which known to be symplectic, smooth symplectic variety, and some associativity condition which correspond to the gluing of the Riemann surface. So if you consider Moatachika variety for R points times Moatachika variety for S points, you choose one point from each and you consider a diagonal action of the group. And you take a symplectic reduction, and the statement that this symplectic reduction is redefined, and gives the Moatachikawa variety for R plus S minus 2 points. So let me show some examples. So for SL2, so from this associativity, maybe it's difficult to see. You can to obtain Moatachikawa variety, you find it's enough to find Moatachikawa variety for 3 points, because if S is R is 3, you increase S by 1 by this associativity. And for 3 points for SL2, this is quite easy. So it's just C2 tensor C2 tensor C2. So for each C2, there is a natural action of SL2, which is a Hamiltonian, and which induces the 3 commuting action on this variety. But if you consider Moatachikawa variety of 4 points, you find something interesting. It's a variety with 4 commuting action at SL2. And this is isomorphic to the minimal nilpotent orbit closure in D4. So why D4? Because you find 4 commuting SL2 action on its affine linking diagram. So the non-triviality of this Moatachikawa variety is that first of all, it's a singular variety. And also, you somehow end up with D4, also you are considering A1. And this associativity condition means that this minimal nilpotent orbit closure in D4 is obtained from this symplectic vector space by the symplectic reduction, which is quite non-trivial, at least for me, but this is well-known isomorphism as the ADATM construction of the minimal nilpotent orbit closure in D4 of HTC. And for SL3, for 3 point, it's already non-trivial. It's a minimal nilpotent orbit enclosure in 6. And why E6, you find a 3 commuting action of SL3 in its affine linking. But you cannot continue like this forever because you go outside of a linking diagram. So this is a completely new family. There's no easy description of Moatachikawa variety, and this gives a completely new family of symplectic varieties. Also, I forgot to write, but these are known to be symplectic singularity, at least for type A, because they are known to be isomorphic to the Coulomb branch star-shaped fiber. And you can ask, so there's a case of a Higgs branch, but what you can show that there exists a unique family of a vertex algebra which satisfy the properties that is required for vertex algebra associated with this class S theory, which is, I don't say, but similar to the one for more logical variety. So there are some Hamiltonian action of group is replaced by Katsumori group action, and there's some initial condition and also some associativity condition. And moreover, associated variety of this vertex algebra is the more isomorphic to the more logical varieties. So by this uniqueness statement, this must be isomorphic to the vertex algebra coming from class S theory. And the last statement means that the beam rastri conjecture on the coincidence of the Higgs branch with associated variety is true in this case. Any question? And so I explained for each complex reflection group, you can associate some simplex singularity by considering some orbifold. And there's some related conjecture by Monetti, Meneghelli, and Rasti, who are again physicists. They say that for any complex reflection group, there should be a vertex superalgebra with the following properties. So first, for its associated variety is isomorphic. So I'm sorry, that's many mistake. This must be the vector space associated with the complex reflection group. So this is a simplex singularity associated with the complex reflection group. And some other property I don't think I should explain in detail. The first, but let me say that this central charge should be expressed by a fundamental invariance of this complex reflection group and some other conditions. And so when complex reflection group is a wide group of simple algebra, so this vertex algebra is supposed to be the vertex algebra coming from four-dimensional n=4 super-Yang theory with gauge algebra. So the point is that it was enough for the 4D theory to have supersymmetry 2 to define this map. But if it has n=4 supersymmetry, then resulting vertex algebra has extra supersymmetry so that this becomes a supervertex. And it's known that the Higgs branch of this super-Yang theory is isomorphic to the simplex singularity associated with complex of this wide group. And maybe I skip this. And so this conjecture is still open, but you can try to do something for the easiest case, which is a case for type A. In this case, wide group is symmetric group, so that the corresponding symplectic singularity is essentially the symplectic power of C2. And it's very well known that this symplectic singularity is resolved by the Hilbert scheme of n points on C2. Because this is a singular variety and this one is a smooth variety, it's much easier to work on this smooth variety. And what you can do is that you can construct a sheaf of vertex superalgebra on this smooth variety. And if you take a global section, you obtain vertex algebra which satisfy the required properties. So in this case, in this way, you can show the existence. You can prove the conjecture of Moneghelli or, but yeah. And so what I don't have time to explain, but what is interesting is that it's quite important to have the supersymmetry in this setting. If you naively construct C for vertex algebra without adding fermions, you don't succeed. You have to add some proper number of fermions to construct C for vertex algebra. And in this case, you can compute the character explicitly. And it's given by this formula. And this indeed a quasi-modular form of mixed weights. And it coincides with generalized Q multiple zeta values introduced by McMahon. So this vertex algebra have some interesting character. And so because the Hilbert scheme of points in C2 is also isomorphic to the Nakajima quiver variety associated with the Jordan quiver. And so we indeed use the Nakajima's construction to construct the shapes. So it's natural to ask whether our construction generalized to other Nakajima quiver varieties. And we expect our method works for any cases, and which is supposed to give the A twisted boundary of the corresponding 3D quiver gauge theory, which was discussed in the paper of Koman, Shin, and Yamazaki. So, a bit early, but I finished.
Thank you. Questions?
Can you explain the unicity theorem in your construction?
Which case?
The more Tetrikawa.
Yeah.
Why is it unique?
So it's so the way I constructed was so maybe it's better to show for vertex algebra setting, we also have the similar initial conditions. So this vertex algebra for 2 points and 1 point already fixed. And the way I constructed is to recover the one for more points from this smaller point. And then it somehow determines unique.
Okay, can you go to page 22?
22.
Yeah, I would like to ask about the statement of the theorem. Can you explain a little bit about how the Schiffer vertex superalgebra is constructed? And is there any interpretation of the associated canonic filtration?
So this is exactly the same as Nakajima's construction. So Nakajima constructed as certain Hamiltonian reduction. And so to do Hamiltonian reduction, you start with wide algebra. Sorry. I was talking. So it's a natural generalization of the work of Kashiwara and Rukiue, who quantized the Hilbert scheme of points of C2 to obtain the spherical Daha.
Okay, okay.
So they start with wide algebra upstairs, and you do Hamilton reduction to get some shape on Hilbert scheme. But you can, there is a natural affinization for wide algebra, which is called beta gamma system. And then you do similar Hamiltonian reduction to get the sheaf downstairs. But somehow you have to add some BC system as well. So roughly speaking, we need to so Hilbert scheme correspond to the Jordan quiver of this type. So this Nakajima quiver variety is isomorphic to the Hilbert scheme. But instead, we consider this kind of super quiver variety. So you add the Fleming vector, you change Fleming vector space to vector space of super vector space of dimension 1, 1. And you do exactly the same and you get this kind of shape.
Okay, thank you.
More questions?
Is there quantization of these more Tachikawa spaces? Just about
You should take, for example, you can take Zoo's algebra.
take what?
Zoo's algebra, which gives quantization. It also, yeah, for type A, it's equivalent. Yeah. So there has been constructed.
More questions? No. Let's thank the speaker again.